working with technology. I'm literally like a 70-year-old grandma. Like, if you've ever tried to explain the internet to your grandma, that's probably how it feels when I use WebEx. I don't know what it's doing, but we're just gonna deal with it. All right. So let's get started. NMR is hold on, sorry, my brain just completely disappeared. So NMR is a type of spectroscopy, and it's basically telling us how things are connected, right? So when we are looking at a basic compound, like the ones I'm going to draw now, we are looking at how things are connected and the framework. So we can't necessarily tell what functional groups there are from NMR, but we can tell how things are connected. Something that you guys have learned about previously was IR, and IR is basically telling you the functional groups. So these are different types of spectroscopy that tell you different things, but they can be used together in research labs. Also, someone asked, are we allowed to view your recordings? Yes. I mentioned this to the last group, so if you heard this already, I'm sorry, but Canvas is a little bit weird for the tutoring sessions because you guys don't get to sign up for it, so I don't know if you can view it directly on Canvas. If not, I will send you guys the link so you can view it. But I will figure it out. We'll see how the tutoring thing goes. You are very welcome. All right, so first and foremost, the first thing you need to know for NMR is what it means to be NMR active. So in order to be NMR active, you need to have a spin state. And Dr. West will tell you for like 45 minutes what a spin state is, what the resonance is, all this different stuff. All you basically need to know for the purposes of testing on the exam is that it boils down to the number of protons and neutrons. So in order to be NMR active and have a spin state, you need to have an odd number of protons and or neutrons. So if you have one of them, that's sufficient. If you have both, that works too. So for example, I'm going to zoom in. We have hydrogen 1, and we're going to look at different isotopes here. So I want you guys to remember, when we have isotopes, we're not changing the number of protons ever, we're only changing the number of neutrons. So if we compare H1 and H2, also H2 is known as deuterium. We're going to pretty much refer to it as deuterium from now on, but I do want you to realize that's just H with a neutron. So it's going to have 1 proton and 0 neutrons in its ground state. And deuterium will have 1 proton and 1 neutron. So since the number for all 3 of these is odd, both of these guys will be NMR active. This is different than carbon 13 versus carbon 12 because carbon has 6 protons, carbon 12 has 6 neutrons, and carbon 13 has 7 neutrons. So carbon 12 has an even and an even number, so this will not be NMR active. Versus carbon 13 has an odd number of neutrons and an even number of protons, so that will be NMR active. If we look at carbon 14 versus carbon 15, we're going to have 7 protons and 7 neutrons. So we have double negative. We win. For nitrogen 15, we have an odd number of protons, an even number of neutrons, so this is still active. So does that trend sort of kind of make sense so far? Yes? Okay, cool. This is one of those things that it's a pretty fairly straightforward concept. So when it shows up on the exam, it's like, 3 points. All right. So the two types of NMR that we're going to talk about in this class are hydrogen 1 and carbon 13. There are a whole bunch of different ways, like atoms we can do NMR on, but for the purposes of this class, only these two need to exist to you. For both of these types of NMR, we have a specific solvent and calibration standard that we use. And usually if he asks you about these questions, it'll be like a matching section. So keep in mind which is which. So the solvent we used is going to be deuterated. And all this means is that we don't have any hydrogens. Instead, we have deuterium. The most common one we use is CdCl3. And the reason we use a deuterated solvent is because, as you can see here, deuterium is active on NMR, but it has a completely different spectrum than H1 and carbon 13. Therefore, it's not at all going to interfere with your signals for the actual molecule you want to test, and it's only going to serve as a solvent. If you're in lab, this doesn't really work out this way, and you get a lot of mess because the lab equipment isn't the best. So if you're in lab, the things I say here are idealized and it might not transfer to the lab. So I apologize. But if you're not in lab, completely forget what I just said. Everything I said is law. Okay? All right. I don't even know if they're doing Orgo Lab this semester, so I don't know if you have to worry about that. But if you guys are in lab, let me know. You are? I am so sorry for you. Orgo Lab sucks, but it's not as bad as people make it out to be. It's not impossible. And I took it over the summer, so summer is not too terrible. Yeah, the single tier. I'm fine. If you ever need help with the lab, let me know. There's not too much I can help you guys with, but like as far as like actually doing the lab report. But if you guys need help with concepts or advice or whatever, I got you. All right, back to what we're doing. So now that we know what kind of solvent we use, we're going to talk about the calibration standard. So the calibration standard is TMS, which stands for tetramethylsilane, and it looks like this. She's a little bit ugly, but that's okay. So basically, this is going to be our 0 point on our spectrum. And the 0 point is basically the most shielded it gets. And so this is an inorganic molecule. So these carbons are going to be super, super, super dense with electrons. They have a whole bunch of electrons. And therefore, we use that to kind of make sure everyone's on the same page, everyone's NMR spectrums line up, because they all have the same 0 point. Again, solvent is deuterated, calibration standard TMS. And now we're going to get into like the real NMR stuff. So the four main aspects of NMR are number of signals, the multiplicity, aka splitting, chemical shift, and integration. So briefly what each of these things are. The number of signals is exactly what it sounds like. That's just how many unique carbon or hydrogen environments we have. Multiplicity and splitting is what tends to be the hardest thing for students. So we're going to spend a little bit of time on that in the next week or so. But basically, it's telling us the number of unique neighbors that we have. And one thing to keep in mind, is that in order to be considered a neighbor, it has to be within 3 bond lengths. And something I like to call the heteroatom rule is that you cannot split through a heteroatom. So when you're doing a neighbor splitting kind of thing, you do not go through a heteroatom. To my people in the lab, you may have to split through a heteroatom in the lab, but they will specifically tell you when you do that. So It's annoying, but it be like that. So if they tell you that it's a pure sample, that's the only time you would split through a heteroatom. But as far as lecture goes, never go through a heteroatom. Okay, and the last rule we have for multiplicity and splitting is n plus 1. So we're always going to do examples, but n is essentially the number of unique neighbors. Chemical shift is pretty straightforward. It's basically just where something is on a spectrum, so what the number value is. And that is going to correspond to how shielded or de-shielded something is. Last but not least, we have integration. So integration is like the most straightforward thing. But students sometimes get mixed up with it. So integration is essentially just the number of hydrogens or carbons that we have in each signal. So I'll show you an example, but it's also defined as the area under the curve. As far as lecture goes, don't worry about that definition. He's not going to make you measure the area under a curve. You just have to know the number of hydrogens or carbons per signal. Are we cool with this so far? Any questions? Comments, concerns, any such thing? Okay. If not, we shall do some examples. So this is something that we already went through, so I should have erased the answers already because it won't be any fun to go through it now, but I'll just explain what we have written already. So basically, if I gave you these two molecules in each set, you have to tell me what type of spectroscopy I would use in order to tell the difference between the two. In the case of number 1, we decided that we could use IR and NMR because, first of all, we have these two different functional groups. So IR is useful to tell the difference between functional groups. We also have this hydrogen, these hydrogens, and this hydrogen, which are all vastly different from one another. So since there's such a big difference in the way the hydrogens are connected, we can also use NMR. In number 2, we're only going to use NMR because we have the same number of hydrogens and carbons. The only difference, we have the same functional groups and we have the same number of carbons. The only difference is where the OH is placed. So in this case, it's a secondary alcohol, and in this case, it is a primary alcohol. So IR would be useless here. In this third example, I'm going to erase this stuff because that's not important for now. Basically, the difference between this molecule and this molecule is a functional group difference. So here we have an amine versus here we have an alcohol. Therefore, we're going to use IR only. Someone brought up a very good point of why couldn't we use NMR because these hydrogen, I don't know why it keeps erasing. These hydrogens and this hydrogen are going to be a little bit different. And basically, the reason we don't want to use NMR is because they're so similar. So like almost everything between these two is exactly the same. It's just a one hydrogen difference. So that one hydrogen is going to be really hard to distinguish from everything else. So an NMR spectrum would be really hard to use to tell the difference between these two. So we're going to stick with just IR. I know that was a lot. Any questions? Also, I have been told that I talk really fast. So if I'm ever talking way too fast, let me know. If not, we can move on. All right. So something we did here was kind of like another quick summary to help you remember what's going on in NMR before we do actual examples. And so we took our propanol and we started from scratch and we basically graphed this whole thing. Before we do that, I want to show you this right quick, which I'm going to actually make a new page because it's starting to look real ugly. The page. Well, it's going to really bother me that this stuff doesn't line up with the dots, so I'm just going to also get rid of that. Okay. So let's say we have a spectrum, right? ppm is the x-axis, and this side of the spectrum is going to be upfield, and this side is going to be downfield. So D and D go together, so this is going to be D-shielded, and this side is going to be shielded. And depending on whether we have a carbon NMR or a nitrogen NMR, or I don't know why I keep saying nitrogen, a carbon NMR or a hydrogen NMR, our range is going to be a little bit different. So on a carbon 13 NMR, our range will be between 10 and 220 ppm. For a hydrogen 1 NMR, our range is going to be approximately 0 to 12 ppm. So just for simplicity reasons, I'm going to do 0 to 12 and call this a hydrogen spectrum. All right, so we know that the left side is downfield and de-shielded. This side is upfield and shielded. But what the heck does that even mean, right? So the way I like to explain it is like this. So let's say these green dots are our atoms, right? And this pink stuff all around it is our electron cloud. So if something has a lot of electron density, a big, thick electron cloud, it's like it has a big brick wall surrounding it, right? Versus this guy has a little tiny amount of electrons, so it's almost like he has a picket fence around him, right? If there's a war going on, and you're either in your tiny little picket fence or you have your big brick wall around you, that's really going to make a difference for how much of this impact you feel from the war, right? So the more shielded you are, the more protected you are. Same thing with these molecules. So we have a harsh environment in this magnet, right? And if we're throwing arrows or frequency or waves or whatever, however you want to think about it, if we throw 4 different arrows at the super shielded one, 3 of those 4 arrows are probably going to bounce back and go away, and only one of them is really going to hit it because it has a lot of protection. Versus this guy, if you throw 4 arrows, most of them are going to hit it, and maybe one will bounce back. So the more it feels the outside, the higher the number will be. So this guy is super, super shielded, which corresponds to having a large amount of electron density. So he will feel less of the less of the environment. Therefore, it will be a smaller number on the spectrum. So it'll be over here, towards 0. This guy, however, is not very shielded, not a lot of electron density. Therefore, he feels a lot of what's going on. All this stuff is hitting it, right? So it has to have a higher number on the spectrum, and it's all the way over here, towards the left. So that's kind of how I like to think about shielding. Does this sort of kind of make sense a little bit?
Yeah, it makes sense.
Yes? Okay. I heard someone else unmute for a second. Okay. So I will leave this up for like another couple of seconds if you want to take a picture or something. If not, we'll move on in just a second. Sorry if you guys can hear stuff in the background. Um, people are just very loud. Okay, so let's go back up here and let's talk about this. So for our propanol example, we went through and first counted signals. So we counted 4 unique signals here. 1, 2, 3, 4. And the next thing that we did is decide which one is going to be the most shielded versus which one would be the most de-shielded. So we see that we have this oxygen here, right? The oxygen is super electronegative, so it's taking a lot of electrons. So the closer you are to the oxygen, the stronger this effect will be, and the more de-shielded you will be. So between all of these guys, the closest one to the oxygen is the most de-shielded. So which one do you guys think will be the most de-shielded? You can either say the color or the number. I'm going to do an awkward dance until someone says something. If you don't know, you can say I don't know. I just need something.
I'm laughing over here. Number 4.
Yes, number 4. Awesome. Okay, so since this one is directly attached to the oxygen, it will be the most de-shielded. That's why it's all the way over here. The next most de-shielded is blue because it's the next closest, and then so on and so forth. And yes, someone just said that in the chat. You almost beat me to it. So yes, the reason green is a little bit more de-shielded than blue is because green is directly attached, and then blue is on a carbon that's attached to the oxygen. So it's a little bit further away. So the order would be green, and then blue, and then purple, and then red would be the most shielded. And basically what that means is green will be the farthest to the left, and red will be the farthest to the right. The next thing we did is we figured out what the multiplicity and splitting was. And the way we do that is we count the neighbors. So I'm going to erase some of these lines just so I make sure you guys are all familiar with some of the rules. So starting with the red guy, we are going to figure out how many neighbors he has. So how many bond lengths can we go through to find a neighbor?
3.
3. Awesome. So we have, let me do that in a different color actually. So 1, 2, 3. We found a neighbor. 1, 2, 3. No neighbors on that side. So the red signal will have these 2 purple neighbors. That adds up to 3. So we get a triplet. Next, the purple one. The purple is a little bit more social. It's in between these 2 carbons now. So we can count, I don't know why it did that. Whatever, we'll just use a different color. This is about to be a mess, but that's fine. So we have 1, 2, 3, and we have 1, 2, 3. So we have 3 red neighbors plus 2 blue neighbors plus 1, just because that's what we do. So altogether we get 6. And so 6 neighbors, we can call that a sextet. That is the most correct name. But scientists are lazy sometimes. So if you have anything more than 5, we also can just go ahead and call that a multiplet. That will suffice. So this is a sextet or a multiplet. So the blue one has 1, 2, 3. So we know it has these purple neighbors. And then on this side, 1, 2, 3. But this is a heteroatom, so you cannot, for the purposes of lecture, go through the heteroatom. So this guy does not count as a neighbor. Therefore, the blue one will be a triplet. I just said we cannot go through the neighbor, we cannot go through the heteroatom. So this green guy is all alone on his own island away from everyone. So he is a singlet, forever alone on the other side of the oxygen. It's a sad life. Sorry. Okay, so now when we start drawing things out, the reason I even drew this out was really just to get you guys familiar with these shapes. He's not going to make you draw a spectrum on the exam, but it's useful for you to understand kind of like what these things look like. So, we started with the green signal all the way to the left, and we have a number 1 on top of here, and that number 1 is the integration. And the integration is just talking about how many hydrogens there are in that signal. So as we can see, 1 hydrogen corresponds to a number 1. He could also show you that with this little squiggle. He doesn't usually, but all that means is that this compared to this is half of the height. So this is half of the integration of this one. That whole thing is kind of weird. Don't worry too much about it. I just include it so that you guys can't be like, oh, you never told us about that. Sorry. I love doing my student voice. Please don't be offended by it. Anywho's, moving on. So the blue signal is going to be a triplet, and so it's going to have these 3 little peaks. The sextet is going to have a bunch of these little peaks. Again, the triplet is going to have 3 peaks. The number of these little peaks corresponds to the splitting, not the integration. So the red guy is a triplet, and this number 3 is because there are 3 hydrogens in the signal. The purple guy has 6 little peaks because it's a sextet, but it has 2 as the integration because there's 2 hydrogens. Again, that was kind of a lot. Any questions? Okay, so someone asked, do we have quizzes for Orgo 2 Lab, or is it just long, detailed lab reports? That's a great question. I'm going to feel so old when I say this, but I took this a long time ago. So I know they changed things a lot, especially with COVID. So I don't know exactly how it is, but when I took it, we had a quiz the first day of each lab. So some labs will be like 2 periods long, some of them will be 3 class periods long, some of them are just 1. So on the first class period for each lab, they give you a little quiz. As far as the lab reports go, they are super long. They're so long and there's so much work. The biggest advice I can give is, first of all, talk to your TAs. They are willing to help you if you are willing to like reach out to them. So for sure do that, and usually they'll give you a lot of pointers. Also, what is it called? I forgot what I was trying to say. Oh, yes, they give you a lab manual. Make sure you read exactly what you need to submit in your lab manual because sometimes they try to trick you and people lose a lot of points. Okay, so in the chat, people were talking about it. Everything should be back to normal in person in the fall. Uh, they don't have online options anymore in the fall. But for now, it seems that if you are online, you have the class period to do it. Like it's just due sometime between that class period. And then if you're in person, you have the entire day of your lab to do it. So I hope that's helpful. All right. Any other questions? Comments? Concerns? Again, I didn't give you guys this spiel for the second hour, but like tutoring is much different than SI. Like in SI, I usually come in with like a lesson plan. I know what we're going to do. I kind of lead the discussion. But for tutoring, it's completely whatever you guys want. So ask whatever kind of questions you want, bring up whatever kind of topics you want. It's all students, whatever. Yes.
I have a question.
Cool. What's up?
In his Thursday lecture last week, he said that we might have to know how to interpret these between ppm and ppm and hertz, I believe. I don't know. Let me pull up my notes here.
Yes, I know what you're talking about. Okay, we can definitely do an example of that.
He even said it would be a couple of questions on the exam.
Yeah, he usually has one or two possibly questions like that. So let me pull it up. I actually do have it in the handout. Also, I forgot to mention this to you guys. The handout that I'm using is the same one I'm using for SI, and you can find it in the Canvas page under handouts. So in case you have no idea what I'm doing. And on page 4, or no, just kidding, page 3, here's an example. So what you're basically talking about is how to convert between ppm, hertz, megahertz, all that kind of stuff. And the equation we're going to use is ppm equals hertz over megahertz times 10 to the 6th. So 10 to the 6th is just here to help you like fix the mega versus just hertz. So for the purposes of actually doing this, I want you guys to pretend this doesn't exist. I just give it to you guys so that you know that it's there, but you guys are not going to do it. Sorry, I don't know why that happened. Sometimes people will do it times 10 to the 6th and get super confused. Please don't do that. So ppm is going to give us ppm is the chemical shift. The megahertz is the frequency of the spectrometer, and hertz is basically the observed frequency. So this is I'm just going to get rid of this part so it doesn't confuse y'all. All right. So that being said, in this example, it gives you the ppm and it gives you the megahertz. So you get 1.25 equals x over 400. And so now you just do basic math. You multiply 400 by 1.25 and you get, does someone want to, I think it's
500.
Yeah. Wait, what was I doing in my head? Never mind. I was like, it'll be 5,000 because I did the times 10 to the 6 thing that I told you not to do. Um, I
But
needed
it's 500 hertz or is it megahertz? Hertz, right?
hertz, exactly.
Okay, that makes sense.
Hmm. And then I don't want to make up a new example, actually. I was going to, but then I was like, I'm just going to give you weird numbers that won't work out. Um, you can use a calculator for the exam, I believe, but it's going to be super straightforward math. Um, so yeah. Someone in the chat said, I know how to read the data a little, but not how to draw the molecules from there. So this is probably a good thing. The exams are going to be multiple choice, right? So that means you won't actually have to like draw out a structure just from reading the spectrum. Um, all you have to really figure out how to do is like you have to understand what's going on. I'm trying to explain this without sounding like annoying. So you don't have to necessarily look at the spectrum and be able to figure out like, oh, this is how you draw a structure based on these peaks, right? You just really need to know what each aspect of NMR is so that you are able to just do like test taking skills, right? Because if you have multiple choice, it's really easy to like kind of go through the answer choices and like throw out all the stupid answers and then work from there. Um, we'll go over a bunch of examples so you guys know what I'm talking about. But yeah, you don't have to like look at a spectrum and know exactly how to draw it. Was basically like the main point. Any questions about that? I don't even know if that was like a great answer. I just it's already like 5 p.m. or 6 p.m. and my brain is so gone. Okay, so the next question. Sometimes when I'm talking, I forget that this is recorded. Like people are gonna watch this later and be like, all right. So someone said, so we do not need to read the textbook intensely, but to do the practice problems he provided in the files in class, we just need to know how to read the graph or calculate hertz. So yeah, the textbook, I'm not saying it's not useful, but it gives you a lot more information and a lot different information than Dr. West does. So, what I recommend you do is just base your studying and your answers to the practice problems off of the information that's outlined here in these handouts and in his lectures. So, everything you need to answer questions for exams and stuff will be based on his lectures and his PowerPoints. So let me give you an example. That's not what I wanted. There we go. You guys are really watching me trying to figure out how to use technology. Wonderful. Okay, so these are the practice problems I'm talking about. And in these practice problems, he gives you stuff like this, where he's like, here's the spectrum, draw out the molecule. No, you don't have to do that. But what you do have to do is questions like this, where it gives you a spectrum and you have multiple choices and you figure out which one it is, right? And so these are a little bit more advanced. Like this is what I would do in the exam review or something to put all the information together. But if you guys want, I can kind of sort of show you what I mean by putting things together. Would you guys want to do that or wait? a little bit. Also,
Yeah, it would be great if you could do an example. That would be awesome.
okay, sweet. So this one's a little bit complicated, so we're not going to do this one, but let's do a sort of complicated one. No. You know what? Fine. We'll do this one. I don't feel like looking for like 20 minutes. Aha, there we go. All right. So the first thing I want you guys to notice is these numbers. So we start at 0, we have 3, so we end at about 5, right? So 5 is what the end of what range, I should say, or what region? So the end of this is approximately 5. So 5 ppm would be towards the end of which chemical shift region? I know we didn't cover all of them, but we talked about this one.
Heteroatoms.
Awesome. So everything we have, we know it's going to be between alkyl and heteroatom. So I'm going to say alkyl, heteroatom. I don't know why I made that so ugly, but it's fine. So, right off the bat, the other thing we can look at is the number of signals. So we have 1, 2, 3, 4 signals, right? And so when we look at the answer choices, what was the first thing I told you guys to look out for? Starts with an S.
Symmetry.
Symmetry. Awesome. So we have symmetry here. We have symmetry here. We have symmetry here. And we have symmetry here. Right? So let's start from the top. We have 1 signal. This is 1, 2, 3, 4, 5. So this has 5 signals. We can automatically get rid of it. Next, we have 1, 2, 3, 4. That checks out so far. 1, 2, 3, 4. That checks out so far. 1, 2, 3, 4. That checks out so far. 1, 2, 3, 4. All right, so the only one we've eliminated so far is A. Now, we can look at the integration. So we have 6 hydrogen, a 2, a 3, and a 3. So a 6 tells you that there is symmetry somewhere. So here, I didn't mean to do that. Okay. So here we have 3 and 3. So these two together, that is so ugly. I'm so sorry. So this and this is 6H. There we go. I am sorry. It's being so difficult on purpose. I'm just gonna come back over here. All right. Anyways, you didn't see any of that just happened. So this and this together make a 6H. Here we have 2H, 2H, 3H. So far, it checks out. Here we have 3, 2, 2, 3. So that does not have a 6H. We cancel it out. Here we have 2H, 6H, 1H. Just kidding, I lied to you. There's no hydrogen there. And we have 3H. So this does not check out because we only have 3 signals and we don't have a second 2H. So this gets thrown out. And then here we have 6H, 3H, 2H, 3H. So we are now stuck between this and this. Oh wait, even easier than that. I forgot to write that we have 1 extra hydrogen here. So that's actually 5 signals. So you can also get rid of this one. Sorry, that was kind of a mess. Usually when I have these drawn out, they're like super big, so they're not hard to see. So I apologize if that was confusing at all. But does the way I went through it sort of kind of make sense?
Yeah, it makes perfect sense.
Cool. Okay. So I think we're going to stop there for today because it is 5:55. Does anyone have any questions, comments, or concerns to end the day? If not, I will see you all next time. Okay, wait, hold on. It said that the blue X is the right one. Okay, that's cool. 1 second, let me look through it. Oh, okay, hold on. Let me redo it, but draw it really, really big. Thank you for letting me know. I was actually going to look at it right after the session to make sure everything was fine. And if that ever happens and I'm wrong, I will send you guys like an email with like the explanation on what was wrong and how to do it correctly. Basically, we cut these ones off. And when we're stuck between these two, the mistake that I made is I thought this was a hydrogen, not a methyl. So let's go back to the point we were at. We have 6H, 3H, 2H, 3H, and then here we have 6, calm down. Why are you being this way? 6H, 2H, 3H, 3H. So at that point, you would look back at the spectrum and you would see, okay, all 6 of these hydrogens are in the heteroatom region, whereas these 6 are all in the alpha region. These 6 are all in the heteroatom region. So between these two, this would be the correct one. I am sorry for any confusion. We will go over this one in SI also next week. But does this make a little bit more sense now that it's a little bit bigger? Yes? Okay, cool. Thank you very much for pointing that out. Goodbye for real now. I hope you guys have a great day. If you have any questions, I'll stick around for another minute or so, but I am going to stop the recording.